Já. Okay, welcome to the afternoon session of the plenaries. So this afternoon we have a short program because of there is a match of two very weak teams in a in a competition that nobody cares about. Anyway, so it's a pleasure to announce Kentaro Saji from Kobe University, who's going to talk about geometry of current two singularities of fronts.
Thank you for the introduction. And first of all, I would like to thank all of the organizers and staffs to give me this opportunity to this Cidinha memorial workshop. And also, thank you very much to change the time of my talk. Then I will never extend the time. Then let me start. The title of my talk is Geometry on crank 2 Singularities of Fronts. So I'd like to start the definition. And the goal of this talk is study the local and global geometry on D4 plus minus singularities of fronts. For local part, F is a germ from 2 space to 3 space, and global part, F is a map from a closed 2 manifold to R3. And they are abstract generalization. And I start with the definition of front and this singularity. A germ from 2 space to 3 space is a frontal if there exists a unit vector field nu, this one, from the same space to unit sphere in the R3, such that this condition holds. This implies that this vector field along F is a normal vector of F, so this vector field is called the unit normal. Then a frontal is a front if this pair is an immersion. A map, not germ, or a map from a 2 manifold to 3 space is a front if for any point on the source space, the germ at that point is a front. And on this condition, this normal condition is equivalent to the map, this pair is from 2 space to the unit tangent bundle equipped with the canonical contact structure is isotropic. Then this F, if this is isotropic, this F, and if this is also immersion, then this F is a projection of a kind of wave front set. So the name frontal or front came from this this setting. And by Arnold Zakariukin's result, from 2 space to 3 space, if this is a front with only codimension 1 singularities, codimension is defined by a generating family, then F is either cathedral edge, swallowtail, or these some singularities, and central singularity of D4 plus minus bifurcation. A cathedral edge is a map germ A equivalent to this map, and swallowtail is map A equivalent to this map. As a central singularity of D4 plus minus bifurcation, for short, D4 plus minus singularity, if is a map germ, which is A equivalent to this germ. This is plus case is this germ, and minus case here. And looking at them, to easily understand, there are no linear terms. So these are co-rank 2 singular points. And this is a picture of this is Castellage and the swallowtail. And these are, I skipped some co-rank 1 singularities. And these 2 singularities are D4 plus minus singularities. This is D4 plus singularity. And this is D4 minus singularity. And I'd like to talk about motivation. Why D4 plus minus singularities are important. Then, first motivation is geometry of co-rank 1 singularities. Co-rank 1 singularities has been well studied in these decades for some curvature or some geometric invariants are defined and studied. And in these studies, it likely understood that standard differential geometric method, classical method, work in directions other than the kernel direction, which means this is a source picture on the map F. If F is co-rank 1 singularity, then there is a kernel direction here on the source space. Then usual classical differential geometric method work on, for example, this direction, not the kernel direction. Then usual differential geometry work. Then the D4 plus minus singularity are only codimension 1 singularities that have not been extensively studied. One reason is maybe the D4 plus minus singularities are co-rank 2 singularities. Namely, every direction lies in the kernel of the differential. Here, this is an image of source space of D4 plus minus singularity. Then every direction at here is the kernel of df. So, usual classical method does not work around this singularity. So, one would like to study singularity of D4 plus minus singularity, geometry on D4 plus minus singularity. Then one have to set up some geometric method to study this singularity. And the second motivation is D4 plus minus singularity appear on several natural differential geometric situations. For example, consider a regular surface with an umbilic point. Then, on an umbilic point, 2 principal curvatures coincide. So, taking a reciprocal of principal curvature and consider a parallel surface of that distance, then the parallel surface have D4 plus minus singularities correspond to umbilic point. And also, D4 minus singularities also appear on minimal surfaces in R3. Let F be a minimal surface given by this form. This is the famous Weierstrass representation formula. And then the singular set is the zero of this function. And F is a front if and only if the differential of this function does not vanish. And it is known that a point is a D4 minus singularity if and only if differential of this function and this function does not vanish. This is a picture on a minimal surface have a D4 minus singularity. So D4 minus singularity and D4 plus singularity appear very natural situation in the differential geometry. And if F is closed to manifold to 3 space, is co-orientable front. Co-orientable means this source manifold is an oriented manifold, and the unit normal vector defined globally. And F has only certain crank 1 singularities. The usual classified swallowtail or these one are included in certain crank 1 singularities. Then this Gauss-Bonnet type theorem holds. This is the integration of Gaussian curvature. K is the Gaussian curvature, and dA is area form. And this is the set of singularities, and this is a singular curvature. And this is another area form. And this is a positive peak and a negative peak. I don't explain, but some algebraic sum of peaks. Then this formula holds. But this formula holds crank 1 singularity. So if we include D4 plus minus singularities into this map F, how will these equations change? This is a basic program. And motivation 4. And an abstract generalization of frontals is a bundle homomorphism. Let E and F be a rank n vector bundles on a manifold M. The vector bundle of the same rank, and take a point. Then this one, let this one be a bundle homomorphism. Then this is an abstract generalization of frontals. The point is a singular point of this bundle homomorphism if this bundle homomorphism is not a linear isomorphism. Then there is a singularity. And this formulation has been studied only when P is a crank 1 singularities. Namely, the dimension of image of this space is n-1. So it's a natural question to include crank 2 singularity in this formula, in this formulation. And so let me start the study of D4 plus minus singularities. Then, but so far there are no effective method to investigate this crank 2 singularities. So we have to set up the method. The method I can take here is constructing SO3 normal form, which is also called Bruce-West type normal form or shortly normal form, and examining its coefficient. The two germs, F and G, are said to be R plus cross SO3 equivalent if there exists a dihomorphism on the source space and a special orthonormal matrix, and this formula holds. If this special orthonormal matrix is diffeomorphism, then this is A equivalence. So now I take here just SO3. So this equivalence preserves the geometric properties. Usually A equivalence destroy the geometry. But considering this equivalence relation, geometry is preserved. And by definition, two R plus cross SO3 equivalent germs have the same differential geometric properties. And for a given singular point, F, this means A class. Among the representatives, a good one, good representative, is called the SO3 or simply normal form. This is a brief history about study of normal forms. For Whitney umbrella case, there is a very pioneering study given by Bruce and West, they constructed this form. Using this form, many researchers studied the geometry on Whitney umbrella. For example, shapes of Whitney umbrella is studied by Bruce West, themselves, and Fukui Hasegawa. And Fukui Hasegawa defined also some blow up on the source space. Taking a blow up on the source space, Whitney umbrella can be interpreted as front, and then studying. And Farid Tari considered geometric foliation on Whitney umbrella. And these one, Hasegawa, Honda, Naokawa, Umehara, Yamada, considered intrinsicity of these invariants. These are coefficient, but by definition of the normal form, these are differential geometric invariant of the Whitney umbrella. So these coefficients can be taken as a language to study Whitney umbrella. For example, this study uses these coefficient as a word. And function on Whitney umbrella and isometric deformation. And geometry of curves along singular point is studied by Hayashi and Hara. And this is brief history to study some normal form for other singularities. Then for Castellage, a normal form is constructed by Martins and myself, and also Fukui. And Osetto Shinha Tari studied function on that. And Caspel cross-cap also. And Swallowtail and SKBKCK for many singularities is given by Fukui Hasegawa. And these considerations are fixed singularity. Then with deformation parameters, normal form with deformation parameter is obtained by Shimada. And she studied behavior of focal conic and some frontalization. And for other studies of singularities, I list here, but I'm so sorry if I miss some your study. To obtain normal form, there is a key lemma. This is the key lemma. D4 plus minus singularities are front, so there exists a linearly independent vector field such that this is a generator of the normal space of the unit normal vector field. So this means this is a generator of the normal space of unit normal vector field. And for D4 plus or D4 minus singularities, one can take a useful basis field of this as this lemma. Let F be a D4 plus singularity, then there exists a coordinate system and linearly independent vector field, these vector fields, such as this holds. And for D4 minus singularity, there exists a basis field and coordinate system, and this formula holds. And this is D4 plus, and this case D4 minus. Then rearranging this basis field, then one can obtain the normal form theorem for D4 plus minus singularities. For frontal, from 2 space to 3 space, satisfying the conclusion, this one. Then there exists a real number and function here, and diffeomorphism and special orthonormal matrix, such that this holds. And for frontal, satisfying the conclusion of this lemma, this existence of these vector fields, then there exists a real number and functions, and the source differ on the source space and the special orthonormal matrix, then this holds. Here, A and B and C are functions. Their 2z are 0, satisfying the following. They must satisfy, setting A is divided by this formula, and U square and V square, and U times U square V square, and V times U square V square, and UV times U square V square, divided A and B and C like this way. And all of them satisfy this formula. Let D be A or B or C. Then all of these functions must satisfy these formulas. On here, this is first coordinate system on the second coordinate and the third coordinate. Then one can obtain normal form theorem. But this formula is unique. Unique means that there are two this kind of formula, and they are equivalent, R plus cross SO3 equivalent, then these functions are the same. But for this formula, the uniqueness does not hold. This is because the difference of this function and this function. This function, the zero set of this function forms a regular sequence in the real case. But in the real case, this zero set is just a point. So by this reason, the uniqueness of this formula does not hold. So here, unique normal form is here. For D4 plus case, even this is unique, but sometimes this is better. We set F plus of some subscript is this formula, and this B30, B03, C30, C03. And for minus case, set like this way. This here and here is the same. And so this is plus. And this are the same. Then this formula is a D4 plus singularity if and only if these three coefficients does not vanish. And if this is a D4 minus singularity, then if these coefficients do not vanish. So for these real numbers and other real number, satisfying A is positive and B30 is positive. These are positive. And the same formula holds. Then these two germs are located on the same orbit of R plus cross SO3 action, if and only if these are equal. And for second case, for these real numbers and another one, satisfying this alpha is greater than 1, and this. Satisfying other one also. Then this one and this one are located in the same orbit of R plus cross SO3 action, if and only if this coincide. So up to 3Z, then we can consider these data data of D4 plus minus singularities. So we call this third order data, this one and this one. Third order data for D4 plus minus singularities. So this is uniquely determined by R plus cross SO3 equivalent class of the D4 plus minus singularities. Then let us start studying geometry of D4 plus singularity. Then F is Fn. Fn is this one. This one. And with this condition, and the nu be unit normal, then the singular set is u axis and v axis. The define gamma 1 is the u axis, the gamma 2 is v axis. So this is a source space, and this is a singular point. And the D4 plus singularity looks like this way. And this curve is gamma 1. And this curve is gamma 2. These are singularity you come to here and here. So these curves form ordinary cusp. So one can define the tangent line of that cusp. This is denoted by L1 and L2. So this is called singular tangent line. And C is a bisector line of the angle of L1 and L2. Here, this is a C. This is called the center line. And C pap is a normal plane, like this way. And nu zero pap is a tangent line, like this way. And the plane generated by C and nu zero, the unit normal, is called the principal plane, like this way. And they are illustrated by this way. This is red one are L1 and L2, and blue one is the center line. And this is the real picture of normal plane. And this is tangent plane. And this is principal plane. Then let us consider geometric information. Let F be the unique version of normal form of D4 plus singularity. Then Gaussian curvature and mean curvature satisfy this formula, can be expanded in this way. This is UV over 1 times some number, 2 or 3 or something, times C30 times C03. And the mean curvature is like this way. And I is a self-intersection curve, because D4 plus singularity have a self-intersection curve. This is, it is expanded by this way. So this is 1, and this is C, 1 over 3 is here. So this is positive. So this is 1 and negative. So the self-intersection curve lies here. So in this way. And looking this formula, Gaussian curvature, the UV over 1 and positive. So Gaussian curvature is, this part is positive. This part is positive. This part is negative. This part is negative. This means that the Gaussian curvature is negative on the where the intersection line exists. So looking this singularity, this part is the region where Gaussian curvature is positive, and always this part is Gaussian curvature negative. always for D4 plus singularity, every D4 singularity have here Gaussian curvature positive and negative. This is a picture of D4 plus singularity. Then you can look, this region is the shape is some ball. And this region can look saddle. This is also some another picture of another viewpoint. Then for other geometric invariant, for kappa S is a singular curvature of kappa Si is a singular curvature of gamma I. Kappa nu I and kappa Ti are normal curvature and cuspidal torsion, respectively. Then we can expand these curvatures in this way. Every curvature is U over 1. So looking this part, cuspidal torsion is bounded if and only if A is 1. A is 1 implies the angle of here, this one and this one are right angle. For Fukui Hasegawa discovered this property is implies the non-versalness of parallel translation of regular surface. So this is another characterization of right angled. This is right angled D4 plus singularity, or is the boundedness of cuspidal torsion of this curve. And looking singular curvature here, then this is U over 1 times B30 and V over 1 times B03. So this implies that the shape of this D4 plus singularity is controlled by B30 and B03. If B30, B03 is positive, then D4 plus singularity curves in this way. The front part is both like this way, and back part is this way. And if B30 times B03 is negative, then this is switched. The front part is like this way, and the back part like this way. This is a real picture of this situation. And this is B30, B03 is negative part. This case, this front part look like this, and this part like this way, and the back part like this way. And this is another picture in this case. So front part look this way, and the back part front part this way, and the back part this way. And the angle theta between L1 and L2 here is theta is obtained by using A in this way, and or also in this way. So this means that A controls the angle of these two tangent lines. Then one can consider the symmetry of D4 plus singularity. And let B is a function of here. This, we set this B. then if there exists an orthonormal group, orthonormal matrix, such that the image sent by the same image as a set jam, then one of the following holds. One of these three holds. If S is a reflection with respect to the tangent plane, or S is a reflection with respect to the principal plane, or S is a pi rotation with respect to the center line. And this parents part specifies F is analytic. If F is analytic, this is the condition of these. The D4 plus singularities has this property. This is we remark that D4 plus singularity is proper, is locally proper. So it satisfies the local properness of the Zakariukin type lemma. So the diffeomorphicity of the target space can be pulled back into the source space. So target diffeomorphism here. This can be pulled back to the source space and then obtain these formulas. And this is a picture when reflection with respect to the tangent plane. This part and this part are symmetric with respect to this red plane. And this is a second case. These parts are symmetric with respect to this plane. So this and this, this and this is symmetric. And this is a third case. The pi rotation of this is this part and this part, this part and this part are symmetric. And one can understand the asymptotic configuration. Consider this form, by this bilinear form. Then a vector field is a solution of this form if this holds. The integral curve of the solution is called the asymptotic configuration. This L and M and N are the coefficient of second fundamental form. Then the discriminant is the same as the negative of Gaussian curvature. So this solution exists only the region, the Gaussian curvature negative. Then for D4 plus singularity, if this does not vanish, then asymptotic configuration is the same as this one. And the picture is in this way. And this is a target picture. Because this part, only this part is Gaussian curvature negative. So asymptotic configuration exists only this part. Only here. Only here. So it is drawn like this way. And then let us proceed to D4 minus singularity. D4 minus singularity, if the FU and FV satisfy these conditions, this is the same as the former lemma, then alpha, the coefficient alpha is given by this formula. By this formula, one can obtain the, since whether the coordinate UV satisfies this condition can be recognized by only by the first fundamental form, because in fact, In fact, coordinate system is satisfied this one if and only if this holds. This function is u square plus v square. So we can obtain this theorem. The invariant alpha is intrinsic because it is calculated by this formula. And the coordinate system UV can be recognized intrinsically. So alpha is intrinsic. And Gaussian curvature and mean curvature satisfy this formula. And looking at this part, the Gaussian curvature is always negative. And the invariant alpha for a minimal surface given by this form must be 1 by calculating this one or calculating this one. Alpha should be 1 for constant mean curvature. And because Gaussian curvature is always negative, there is asymptotic lines. So if f is a front, namely it is d4 minus singularity, namely C21 and C12 is positive, then the asymptotic configuration is the same as this one. The integral curves of this form is in this way. And on the target, we can draw like this way. And then let us proceed to global formula. Then for global formula, the Gauss-Bonnet theorem, it is taking the integration of Gaussian curvature and geodesic curvature like this way. So one need the boundedness of these measures because Gaussian curvature or geodesic curvature is generally diverges at a singular point. So it should be bounded to take integration. So we need the boundedness of the curvature form. Then the Gaussian curvature form, KDA, is always bounded for front or frontal. Then this is a short proof, but I skipped. Then the geodesic curvature form in this way. The S is the arc length parameter of the target curve. Then this form is bounded. This is a proof. And for Gauss-Bonnet theorem, must we consider some inner angle. Inner angle, for example, inner angle here. So along a triangle, for example, like this way. So inner angle at the singular point is needed. And the inner angle must be continuous to tending to this singularity like this way. It must be continuous. So by this lemma, the continuity of the initial vector holds. Now let F be a D4 plus minus singularity and gamma be a curve satisfying some generic condition. Then this vector is an initial vector of this curve along gamma. CT is a curve emanating from this curve. So this is the initial vector of some curve along this curve. Okay, this is gamma, and CT is this curve. And T is here, and T, we want to take T to 0 into this point, then this vector is well defined and continuous with respect to this parameter. Then this is a proof. Then the preparation for Gauss-Bonnet formula is obtained. So let F be from a map from closed to manifold to R3 be a co-orientable front. Namely, this is oriented and the unit normal vector is defined globally. Then take some coordinate agreeing with the orientation. One can obtain this function. We set M plus is this function is positive and this function is negative. This does not depend on the choice of coordinate system. D4 minus singularity is positive or negative if its punctured neighborhood contained in M plus or M minus, because this singularity is isolated. So around this singularity, if it is M plus, then it is positive. Here, then negative. Let dA is the area form in this way, and dA hat is the area form in this way. Then the Gauss-Bonnet type formula folds. Here, this is white part is classical one, and this yellow part is the new part of considering D4 plus minus singularity. If F is a co-orientable front and the singular set consists only of codimension 1 singularity, including D4 plus minus singularity, then this holds. This is for D4 plus singularity, and 4 times this angle, minus 2 pi. And for D4 minus singularity, just count the number of D4 minus singularity times 2 pi. And for this integration, the white part is classical one. And this is an algebraic sum of D4 minus singularities. This D4 plus minus is positive D4 minus singularity. And D4 minus minus is negative D4 minus singularity. So let us consider abstract generalization. Let U be an open set containing the origin, and E be a rank 2 vector bundle. Then this bundle homomorphism, let us consider in tangent space to this rank 2 vector bundle. The point is a singular point. Then if this map is not a linear isomorphism, then this is a generalization of frontals. And this is introduced by myself and with Mehra and Yamada, and followed very generalized by the Medina, Tejeda, and Ruas. For example, let us take a map from 2 space to 2 space. Then taking differential is a bundle homomorphism. And let F be a frontal. And new pap is a subbundle, consists of new pap. Then this is a bundle homomorphism. So by this generalization, one can take this situation. And this is included. So this is a kind of natural generalization. And let det E star be the determinant line bundle, and take a non-vanishing section. Then for some coordinate system, this formula holds. And here, we can obtain the function lambda. The zero set of this function is a singular set. And if rank of this map is 1, then there exists a vector field near this point such that it is a generator of the kernel of the bundle homomorphism. Then a point be a singular point of bundle homomorphism. It is a cuspidal edge point if it satisfies this one, and swallowtail point if it satisfies this one, and D4 plus minus point if it satisfies the property of D4 plus minus singularities. If the bundle homomorphism is constructed from a map, as in example A, in this example, then cuspidal edge point is a fold, and the swallowtail is cusp, and I2 to singularity. It is classified by Liga and Ruas. Then it is D4 plus singular point, D4 plus point. And if the bundle homomorphism is constructed from a frontal, as example B here, this one, then cuspidal edge corresponds to cuspidal edge and swallowtail point corresponds to swallowtail, and D4 plus minus singularity, then the bundle homomorphism is D4 plus minus singular point. So, considering this abstract generalization, one can include some other situation into this formulation. Let this be a connection and consider this bundle homomorphism. But for this one, it is actually just consider vector field as a map from 2 space to 2 space. So this produces no new insight. Considering this one, let G be a metric, and this is identified to this space to this space by this way, and its Lie derivative is also identified with this map by this way. So taking this composition, then this is a bundle homomorphism. And considering this bundle homomorphism, the point is rank 0 singular point if and only if X is this form. And consider X, the second Z of X is like this way. Then this is D4 plus minus if and only if this holds. So this has certain geometric meaning, but it is unknown. But in this way, one can contain some new geometric object in this formulation. So that's all. Thank you so much.
Okay, let's thank the speaker. Questions?
Thank you very much for your nice talk. And I have questions because this generalization of Gauss-Bonnet formula, the first which you proved with Umehara and Yamada, works not only for capital H's to 3, but also to 5. Yes. So do you know any singularity that this Gauss-Bonnet formula does not hold?
I don't know so far.
Okay. So there are only new invariants appears, yes?
Yes.
Yeah, okay. Okay. Thank you very much.
More questions?
So if D minus has negative curvature, can it be uniformized? There is uniformization with in some way with the hyperbolic plane?
Should be.
It should.
Yes.
And another question, if the action of SO3 times R is kind of like conformal geometry, or what type of geometry are we talking about?
Sorry?
The action of SO3 times R is like a conformal type geometry, or what type of geometry does it have?
Euclidean.
Euclidean. Okay, let me play. Thank you.
More questions? I have a question. How much of this, of your, your invariants and everything, how much can you generalize for affine geometry? Because, of course, curvature, values of curvature, these things are not invariant, but signs, proportions, some proportions are invariant. Have you thought about how much can be generalized for affine geometry?
Yes, I think it can be generalized. And for affine geometry, and just as you said, just a sign maybe. And yes, it can be. And maybe third order information is important for affine geometry, I think.
Okay, so if there's no more questions, let's thank the speaker again. Very nice talk.
Just give me 30 seconds. Just 30 seconds. And ninth version of Valencia workshop will be held on this period at Kobe University, Kobe, Japan. Agrandamos a sua participación. This is fixed.
Okay, so reminding everybody that tomorrow it starts at 8:30, right? 8:30, not 9. Okay.
Let me turn off.